Hey folks, it's going to be our last lecture that isn't just an example problem. And I want to talk about conservative forces again. We talked briefly about this last week in chapter 9, but I want to talk about specifically conservative forces when we're talking about our potential energy. Potential energy is defined explicitly for interactions involving conservative forces. All right, if the force is not conservative, then I can't talk about it in terms of potential energy. So what do I mean by this? Let's talk about gravitational potential energy. That's kind of our go-to. Um, Gravitational potential energy is an energy that depends only on position, right? It doesn't depend on the path that we actually get there, right? I don't care if my pencil drops from here to my desk, or if it rolls down a hill and eventually gets down to my desk. As long as I start here and end here, I have the same change in potential energy, right? We can kind of draw that out a little bit. If I consider a starting point, let's call it A, and an ending point called B, and these 2 points are at different heights, right? They're at different heights, some delta y. If I take a path, let's call it path 1, right, from B, and I go maybe down a spiral kind of whoop-de-doo thing here, maybe a little loop, right, and get to A, I have some path, delta S1. Ooh, it's a weird path, and it's kind of long, especially when I consider another path from B to A that's just a smooth slope, right? I think we can all assume that our second path here, delta S2, is a shorter path than delta S1. And yet, when I consider the potential energies of delta UG for path 1, delta S1, it should be equal to, and it is equal to, change in potential for the path delta S2. These are equivalent changes in potential energy. But now let's consider a non-conservative force. So gravity is a conservative force, and it allows me to talk about this in potential energy. If I think about a non-conservative force, like friction, friction actually does depend on how much path there actually is. Because I'm taking energy out of my path all along the path, right? I'm taking energy out. Where's that energy going? We talked about this just for a smidgen last week, but that energy is going into thermal energy of the environment. That's pretty much all we're going to talk about as far as thermal energy goes. But what we're saying is that the work done by friction is taking energy out of my system and placing it into the environment. It's redistributing it into the environment in a very low use kind of way, a very useless type of energy. So if I'm thinking about friction, right, I do a lot more friction on path 1 than I do in path 2, simply because the path itself is a lot longer. And so I have an accumulation of that frictional force, that work done by friction. All right, so work done by friction, right, is not conservative, right, is not the same between these 2 paths, because force of friction is not a conservative force. Right. So again, conservative, we can just think about that as it's not path dependent, it's only position dependent. Where's my starting and my ending points? That is a conservative quantity, right? A conservative path, a conservative energy, a conservative force. Spring forces, right? Elastic potential energy is conserved. Right? It only cares about how I got from. It doesn't care about how I got from part A to point B. It only cares that I did get from point A to point B. whereas something like friction or an applied force might actually depend on the path that we go through. So I want to drive this home just so that way we're all on the same page. I don't care about the actual path when I'm thinking about potential energy changes for gravity or for springs, for elastic systems. I only care about the path when it comes to friction, when it comes to work done by the environment that is non-conservative. All right. So that's going to do it for this this lecture. If you have any questions, again, email or office hours. I want to make sure folks feel comfortable going into next week's exam week with everything under their belt. So yeah, I'll see you in the next. I'll put up a few example videos now. All right, bye.